All right. All right. So it's 10:30. I'm gonna get started. Um, I think this is week 5. Is that right? Okay. So if this is week 5, next week is week 6, which is where we're gonna have the first exam. So what we'll do today is to have a practice exam for the actual midterm or exam one next week. Okay. So that's what we're gonna do today. Let me see if I can set up a reminder on Canvas because Moodle used to have a feature to do that. Um, since we're using Canvas, does it have a calendar? I can do it through the announcement, I suppose. That's the other way to do it. Okay, I'm just going to put it into the announcement, so this way you guys get a message to remind you of the exam next Wednesday. So it's 1 week from today. So I just say exam 1 on, and what is the date of next Wednesday? Let me check that. October the 3rd. Okay. All right. So okay, so it's just a reminder. Details are definitely going to be in today's lecture. So if you want to review, what is going to be in that exam, we just have to go through today's lecture. So it's going to be on everything up to the last lecture. So that means one portion of floating point numbers will be included. Okay, we haven't really quite talked about the conversion using the algorithm, so that part will not be a part of it. But understanding the format will still be a part of it because we did talk about that part. All right. So what I'll do next is I'll give you a practice exam. The practice exam is from last semester, not last year, but last semester. And it's going to be about the same time frame. Last year is not going to be exactly the same. And I will make this available to all of you. So I'm going to share this, into the other folder. And let's see, this is this is the right time. And let's see, I want to make it look a little bit bigger. Okay, there we go. All right, so I'll just go ahead and go through the, this is from last semester, so the time and the date will be wrong. But otherwise, it's pretty much the same setup as your exam. The first thing is it is open book and open notes, but there won't be any electronics other than a scientific calculator. You can choose any scientific calculator, even the ones that can do hexadecimal and binary arithmetics. So even those are allowed. No cell phone though, okay? So, I don't want people to tell me my scientific calculator is an app on my phone. That is not gonna work. So it has to be just a dedicated calculator. The assessment is individual. This part is covered in the syllabus as well. So basically the score, should reflect only the competency of the student with the name and student ID as indicated, above, which is basically the first thing you want to do is to fill that in with your name and your student ID. And I want your last name first, so I want your family name first because that's how Canvas is arranged. So this makes it easier for me to enter your grade afterwards. The answer should be independently and originally derived, which means without assistance from somebody else, within the time that is allocated. So that means once the time is up, I don't want people to keep writing on the answer sheet. Okay, so just turn in whatever you have at that point, because otherwise the risk is I'm not going to take the exam at all. So so the cost is potentially much higher than the marginal point that someone may be getting. No sharing of notes and the book, during the exam. So if you guys want to work on a common notes or paper, pieces of paper to bring in, that's okay. But you have to do it prior to the test. Okay, so let's say the entire class here decides, we'll just sit together and then study together and come up with, the quote unquote cheat sheet together. That's okay with me. It's not a problem. As long as each one of you has your own copy, for the exam, that's fine. But I do not want any type of sharing of any type of paper or book during the exam. All right? Do not discuss the questions with students who may not have taken the exam. So unless you know somebody else has already taken the exam, do not discuss the questions. Okay? You can use additional sheets of paper if necessary. I would say about 10 to 20% of the class usually will need attachment of extra paper. So it can be because of whatever the original answer was, was not valid. So somebody just cross it out, and then there's no space anymore. But I typically leave space for you to answer the questions on the question sheet itself, as you will see later. Write legibly. I cannot give points to answers that I cannot interpret without a post-exam explanation. So if somebody comes back to me and go like, oh, this squiggly line actually means blah, 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 if I cannot interpret it, without asking, without that person volunteering that information, I cannot give points to that stuff, okay? So you just have to write in a way that is legible. When asked for explanation, explain to the point where each step logically leads to the next. So when we see a question like that, I'll explain what I mean by that. Because for the most part, sometimes I do not allocate a lot of point values to the actual answer itself. I allocate point values to the derivation of the answer, because it is the derivation that shows that you understand the concept. It's not the actual final answer that is demonstrating that you understand the concept and know how to apply those concepts. Last time I have every single question having equal weight. I'm tempted to do exactly the same thing. This makes it easier for you to prioritize what question to answer first. Okay, because if they all have equal weight, you look at all the questions and go like, this is an easy one, or this one takes the least amount of time. Get those first, okay? When you see one that's like, that's going to take some time, or it will take me some time to think about this one, push it to the last question. So this way you get all the easy question first, and if you run out of time, at least you get all of those, right? If you try to tackle the more difficult questions first, you might end up with no time to answer any of the other questions. So that's not a very good deal. Is that okay? All right. So I'm very tempted, to keep questions having the same weight. There were 7 questions last time. There's no guarantee whether we have 7 questions or not, because it depends on the difficulty of each question and stuff like that. The first exam accounts for 20% of your actual final grade. Homework, all to get all the homework, all the lab, only adds up to 20%. So that means exam 1 by itself is equivalent to all the homework, all the lab that we do in this class. All right. So are there any questions about, how the exam is set up, or what you can bring to the exam to help you? No questions? All right. All right, so we'll take a look at question 1. This is question 1 from last semester. Consider a binary subtraction involving a 3-bit minuend and a 3-bit subtrahend. So in the exam, I'm not going to answer questions of, what is the minuend and what is the subtrahend? Because those terms were introduced in class, okay? They were also used in the lab. So basically, I'm expecting people to remember those terms, or at least have those terms definition on a piece of paper. So this is why, it is important for you guys to prepare, for the exam, at least have the material, with you. So if you say, I cannot memorize all these things, write it down on a piece of paper, bring that piece of paper with you. Is that okay? Okay. So moving on. Step 1, is it possible for the overall borrow flag to be set and the sign flag to be cleared after the subtraction? Okay, so this is just asking, is it possible? So what kind of answer do you think I'll be expecting? Yes or no? It did not ask for any explanation. It's simply asking, is it possible? Okay? So you have the answer either yes, it is possible, implying it is possible, or no, it is not possible. Leaving this part blank does not imply it is not possible. It simply implies, it simply says, that person does not know what the answer is supposed to be. So blank does not imply one way or another. You have to explicitly say yes or no. Okay, now if you want to be extra clear, you can always say yes, it is possible, or no, it is not possible. So are we okay with that? What is considered clear? Okay, and there's no implicit answer. Okay, step 2. If the answer to step 1 is yes, give me an example. State both x and y as binary numbers. And step 2b is saying if the answer to step 1 is no, explain why it is not possible. So here is the detail, which probably is where most of the points are going to. So if you answered yes in step 1, then you have to go for step 2a. If you answer no in step 1, then you have to go for step 2b. Now, if somebody answers yes in step 1, but then proceed to 2b, I cannot give that any point because the answers within the same question are inconsistent. So that would be like no points. Okay. So in this case, what do you think? Is it possible to have a overall borrow flag to be set, but the sign flag is cleared after a subtraction? Okay, so let's take a look at what that means. Okay, so what I'm trying to do right now is to illustrate, how I would tackle that problem. And I haven't plugged in my tablet yet. Okay, and it's turned off, so I'm gonna have to turn it back on. It's gonna take a little bit of time. There we go. So it's being enabled, being turned on. It takes a little bit of time to boot up. All right, so getting back here. What is the meaning of the borrow flag in a subtraction, in a binary subtraction? What does it mean? Think of it as comparison and not just subtraction. Yep.
Does it mean that the subtrahend is larger than the minor hand?
Yep. So the minuend is less than the subtrahend, but using the unsigned interpretation. Okay. And we can set up a lot of scenario for that to happen. So it's pretty easy to find an example to set the borrow flag. Okay. What about the sign flag after a subtraction? It's a little bit tricky, right? I mean, the sign flag after the subtraction is a little bit tricky because if the sign flag after the subtraction is cleared, it can mean that the minuend is not less than the subtrahend if it's not overflowing. On the other hand, if it is overflowing, it can also mean that the minuend is actually less than the subtrahend. So there are two scenarios in that case. So you kind of have to think about all of these branches. Okay, the borrow flag is easy. The sign flag is a little bit tricky because this question doesn't say anything about the overflow flag. If it doesn't say anything or place any constraints on the overflow flag, it means it can be 1 or 0. You can consider cases where the overflow flag is a 1 and also cases where the overflow flag is a 0. So knowing that, okay, let me see if my tablet is up. It's almost up. It's getting there. All right, so it's getting. Excuse me a little bit here, just so that I can get to the folder. Now everything is getting recorded, so if you need to write down something that is not my voice nor what the screen is displaying, something that you come up with or some of your own understanding, that's something that you might want to write down. Okay, so now that it's up, let me re-enable it. There we go. Okay, so the borrow flag equals 1 kind of implies the minuend is less than the subtrahend. But you have to remember this is using the unsigned interpretation of the bits. Okay, so there are quite a few scenarios where we can set that up. The sign is cleared can mean one of two things. Okay, so there are two ways to proceed at this point. If the overflow flag is also a 0, that means the minnow is not less than the subtrahend, or the minnow is greater than the subtrahend, but this is using the signed interpretation. If the overflow flag is a 1, then the minnow is actually less than the subtrahend, but also using the signed interpretation. All right, so looking at these things, now we have to think about, but how do we find a case, so that this can happen? Okay, so what do you think? How do we set this up so that we can find exactly a case like that? It's a 3-bit number, right? Okay, so what you can do is to say, okay, so we got x2, x1, x0 for our minnow n. We have y2, y1, y0 for our subtrahend, and this is a subtraction. We want to end up with a borrow flag of a 1 here, but we want to end up with a sign flag being a 0 over here. So based on these constraints, okay, what can we do? So then you have to think about some of the cases. If you want to brute force this, you can, because with only 3 bits, how many values can we have for x? 8 of them, right? And how many values can we have for y? 8 of them. So the total number of cases is 8 times 8, which is 64 cases. You can work out all 64 possible cases and see whether it is possible, in which case it fits that scenario. So you can brute force it. Would I recommend brute forcing it? No, because it's going to take a little bit of time. Okay, even if you're very, very good at arithmetic subtraction in binary, it will still take you some time. So that is not recommended. So what I'm going to do is to say, okay, so if that is the case, let me see if I can generate a case where just looking at x2, y2, which are the most significant bits of the numbers, and go like, just manipulating x2, y2, can we end up with a borrow? Oh, that's easy. Because if x2 is a 0, y2 is a 1, that guarantees the borrow flag has to be a 1. Done. Okay, so we know how to set the borrow flag to be a 1 pretty easily. So now the question is, locking down the most significant bits of the minnow and the subtrahend, what about the sign flag? Because 0 minus 1 is a 1 here on the Q row, right? So we need another 1 here so that it becomes a 0. Is that making any sense? So if I were to complete this picture, this is going to be a 1 guaranteed if x2 is a 0 and y2 is a 1. So in order for the sign of the difference to be a 0, I need a 1 here. So that 1 is indicating some x1, y1 or x0, y0 is generating a borrow. So the question is, can I arrange that? What if I make x1 0 and y1 1? Okay, that would also generate a borrow over here. So let's see if that works. x2 is 0, y2 is 1. So that would generate the borrow over here. And what about x0, y0? They probably can be anything we want. So let's say this is x1, y1, x0, y0. We'll make them the same. So now I have a case to test, okay? I don't know whether it works or not, but we'll give it a try. So we'll carry out the actual subtraction, which is 0, 0, 0 minus 1, 1, 0 in base 2. And there's a borrow of 0 here. So by this time, okay, you guys really should understand how this format of subtraction works. Now, you don't have to use exactly this format, okay? But since I use this for explanation, it might be helpful for you to use exactly the same mechanism to work it out. 0 minus 0 is a 0, 0 minus 0 is a 0, so there's no borrow here. 0 minus 1 is a 1 here with a borrow. 1 minus 0 is a 1. 0 minus 1 is a 1 with a borrow. 1 minus 1 is a 0. Woohoo! I got my answer. So do you see how I used the definitions of the borrow flag and the definition of the sign flag to at least come up with a first guess of how to set it up? Is that okay? Yep. Oh, there are many answers. Correct. Oh yeah. There are multiple answers to this question. That is correct. Which also means, if everybody gives me exactly this answer, then I will probably have some suspicion. So is that okay so far with this one? And how I reasoned it out, but it's all based on the definition of the borrow flag and the sign flag. Now, the overflow flag is not used at all here, okay, which gives you a pretty good idea of what is going to be in your exam, because I never used the same question, at least in adjacent semesters. Okay. So that one is done. Moving on to question number 2. Okay. So for question number 2, it's a little bit longer, okay? So let's go ahead and read the question first and make sure that we understand what the question is asking. Let ki be bit I of the carries, okay? That's pretty consistent with the terminology in my modules. Xi be the bit I of I, yi be the bit I of y, in the addition of x plus y. In other words, I'm using the same notation as in my notes, okay, of the modules. In class, we defined k subscript I plus 1 to be xi yi plus qi ki. Okay, that's actually from the notes itself as well. Consider changing this definition to k I plus 1 equals to xi yi exclusive or qi ki. Okay, so I'm only changing the or, which is represented by a plus, to exclusive or, which is a plus with a circle in it, a circle around it. The symbol exclusive or is defined la la la, okay? I give you the actual definition of exclusive or, okay? So step 1 is the new definition going to work in an adder? Okay? Once again, your answer is either yes or no. Okay? If someone leaves this completely blank in step 1, I cannot give that person any points, because it's neither a yes, no, or no, so that's going to be a no point. So 2a says, if the answer is yes to step 1, explain why this will work for all possible cases of ki, xi, and yi. And then in 2b, it's kind of the same deal as in question number 1. If the answer is no in step 1, explain why this will not work. Now, in this case, explaining why it's not going to work is easy. Give me a counter example. Give me an x, a 3-bit number. Give me a y, maybe a 3-bit number, such that, if I use exclusive or instead of or, the answer is going to be wrong. Okay? So does everybody understand what the question is asking? Okay, all right. So what do you guys think? Can we substitute the or with an exclusive or and not change the behavior of the adder? So what is going through your mind? You have to think, what is the difference between the or versus an exclusive or, right? So what is the difference from the perspective of a truth table? What is the only one case when they are different?
And or when there is one in either of them,
Right.
it will be one.
Yep.
An exclusive or if when there is a difference, then it will be a one.
Exactly. So the only difference is when, so 0 exclusive or 0 is 0, but 0 or 0 is also 0. No problem there. 0 or 1 is 1, and it's true for both operators. 1 0 is 1 for both cases. It is the case when you have 1, 1 on both sides that they are different. 1 or 1 is 1. 1 exclusive of or 1 is a 0. But wait, how do we know that? You never talked about it in class. Well, I don't have to. I give you the definition of exclusive OR. So if you work out the exclusive OR, even using just this definition, you will find that 0 exclusive or 0, 1 exclusive or 1 is a 0. So now that you know the one minor difference between the OR and the exclusive OR, then you have to think, in the original equation here, would it make any difference? In other words, is there a case where xiyi is a 1 and qiki is also a 1? Can it happen? It's not possible, okay? And you don't even have to, at this point, you have to explain it, but at this point, you don't even have to really understand the material because we actually talked about this in class. So if you went through the material in class, then you will find out that, nope, that cannot happen. But why can't it happen? I also explained that in class, it has to do with the definition of QI. What is QI? The partial sum of xi, yi, which is the exclusive OR between xi, yi, okay? So that means if xi, yi are both 1s, so that this conjunction itself is a 1, qi is guaranteed to be a 0. If qi is guaranteed a 0, then it doesn't really matter what ki is because the other conjunction is guaranteed to be a 0. What about the other way around? What about if qi, ki is a 1, can xi, yi be a 1 also? Well, let's think about it. If qi, ki is a 1, qi has to be a 1. But if qi is a 1, which is the exclusive OR between xi, yi cannot be the same. So one has to be a 1, the other one has to be a 0, which means xi, yi has to be a 0. So that would be the explanation, is to explain why it's not possible for both conjunctions to be 1s. Now, just stating both conjunctions cannot be 1s will only get partial credit. Okay, so the key connection is QI. You have to use QI in the explanation of why xi, yi and qi, ki cannot both be 1s. Can they both be 0s? Absolutely. Ki can be 0, one of xi, yi can be 0, then both terms are 0. That's not a problem, okay? Because, exclusive OR versus regular OR will still say 0 operator 0 is a 0. So is that okay with question 2? Both in terms of what the question is asking, how I reason this out, and what is considered a good answer. Is that good? Okay. Now you can always come back, and ask additional questions if you find that, okay, wait, hold on a second, there's one part that I didn't quite understand. We can always go back to an earlier question. Question number 3. In the following space, show a binary subtraction again of 3-bit numbers where the borrow bit is set but the sign bit is cleared. The subtraction would be carried in the longhand style where the rows are for x, y, the partial difference q, the borrow bit t, and the difference z. And if you think this combination is not possible, explain why it is not. You can probably see that this is almost a repetition of question number 1. That was actually my mistake last semester, but nobody complained. I didn't hear anyone complain, go like, but this is the same as question number 1. I demand another real, actual, different question. Nobody complained. So you can basically just go for the same answer in question number 1, except this one does require you to use the longhand subtraction to show me the actual subtraction result. Okay? So any questions about number 3? Because I just carry out the longhand subtraction before, so that's applicable here also. Is that okay? Number 3? All right. Number 4. So number 4 is, so this is the actual answer to one example. So what is the base 10 representation of the base 5 number 32. Don't say it's 32.01 because 32 is an actual quantity. It's 32.01 in base 5. In the following space, derive the base 10 representation of the value step by step. In other words, show me how you come up with the base 10 representation of the value, starting with base 5 representation. So what you see here is already somewhat of a shorthand of the actual answer. So I'm going to get rid of this so that it's not, there we go. So I'm going to get rid of that, and I'll use the tablet to do this. But let me copy the question first. 32.01 in base 5. Okay. It's just quicker for me to use the tablet in this case. Okay. So how do you explain this? Well, it is the same thing as 30 in base 5 plus 2 in base 5 plus 0.0 in base 5 plus 0.01 in base 5. In other words, all I'm doing here is to separate the digits into its own term, okay, without the interference with all of the other terms. All right, well, so what is 30? It's 3 times 10 in base 5 plus 2 times 1 in base 5 plus 0 times 0.0, oops, yeah, back, 0.1 in base 5 plus 1 times 0.01 in base 5. So this time I'm separating the quantity from the unit of that particular digit. Is that okay? Do we understand? Can we separate what I mean by the quantity versus the magnitude? Huh? Say that one more time? No, that's right. 1.1 times 0.01. So okay, let me clarify which point is actually multiplication. That's multiplication. Okay. So now I can say, oh, this is 3 times 5 to the power of 1. This is 2 times 5 to the power of 0. This is 0 times 5 to the power of negative 1. And this is 0 times 5 to the power of, oops, that's 1, times 5 to the power of negative 2. So this is where the actual quote-unquote base conversion happens. Because 10 base 5 is now 5 to the power of 1. 1 in base 5 is now 5 to the power of 0. 0.1 in base 5 is now 5 to the power of negative 1. And 0.01 in base 5 is now 5 to the power of negative 2. So this is the most crucial step, because from here on, it's all base 10 numbers. The base 5 stuff is already completely gone at this point. So now we just carry out the actual calculation. This is 3 times 5, which is 15. This is 2. This is 0. And this one is 1 over 25. So now it becomes 17 and 1/25. And you can just leave it as 17 and 1 over 25. That's perfectly okay. You don't have to use the decimal representation. Or if you choose to use a decimal representation, you can always say it's 17.04. Same thing. But at this point, it's a base 10 number. And for base 10 numbers, you don't need to use a suffix because it is understood that any number without the suffix is in base 10. So, any questions about this answer? Yep. Say that one more time. 17, I can't hear.
So wouldn't it technically be 17 over 25?
17 over 25. Why would it be 17 over 25? I can't hear you, sorry.
Because it looks like multiplication.
It looks like multiplication. This is a fraction. Yeah. It's 17 and 1 over 25. last I checked, this is how we express, fractions. Am I mistaken? Okay. All right, so any other questions? No other questions? Okay. All right, so that's number 4. Number 5 is this one. So number 5, I'm gonna erase this first. Okay, so number 5 is asking, what is the base 2 representation of the base 10 number 10.375? So the quantity is 10.375 in base 10. In the following space, derive. So I have a lot of typos in this one. So in the following space, derive the base 2 representation of the value step by step. So it's basically going in the opposite direction. So this time you are given with a base 10 representation of a value, and you have to step by step convert it into a base 2 representation. So what are you going to do? Well, you have to break the value into a sum of powers of 2. Okay. So in your mind, instead of saying, oh, that's kind of complicated, powers of 2. Nope. In your mind, just kind of go with the analogy of 1, 2, 4, 8, $16 bills, and then on the coin side, you have half dollar, quarter dollar, eighth dollar, $16th, and so on. So in those terms, okay, how do we express that value? So we start with 10.375, okay. So we want to express that in powers of 2. Now you can bring your own little table of powers of 2, okay. So we can basically say, okay, 1, 2, 4, 8, 16, 32 on one side, and then we have 0.5 or 1/2, 0.25 a quarter, 0.125 an eighth, and 0.0625, which is a 16th, and so on, okay. That's up to you to decide. If you can generate this list on the fly, it's not a problem. If you say, I want to put it on a piece of paper just in case I don't come up with this list correctly when I'm under pressure, well, put it on a piece of paper. Bring it with you. Okay? So now I look at these values. I look at 10.375 and go like, okay, so what quantities do I need on this side to make up for that quantity over there? We always start with the bigger ones. So we pick out an 8 first, right? If you want to go really, really step by step, you can say it's 8 plus 2.375. Then we go like, okay, what about this 2.375? Which value should I pick as a power of 2? Well, that's kind of obvious, the 2, right? All right, so now we have 0.375 left. So you have 8 plus 2 plus, okay, you look at 0.375 as a base 10 number, and then you look at the list on the right-hand side and go like, 0.5 is too much, but 0.25 will do. Okay, so you say 0.25, and then what is left is 0.125, and then you look at 0.125 and go like, oh, that fits exactly into one of the powers of 2 as well. So we are done as far as converting the value into a sum of powers of 2, including negative powers. Okay. All right. So now what do? We look at 8 and go like, yeah, it's 2 to the power of 3. 2 is 2 to the power of 1. 0.25 is 2 to the power of negative 2. And 0.125 is 2 to the power of negative 3. Now, how do we know that? Well, you can extend your table a little bit. 0, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4. Those are the powers of 2 that will give you the value that is on the left-hand side of that index. Is that okay? If you want to generate a table like this, use a spreadsheet, okay? So that you don't have to do it manually. All right, so now what do? Then we actually do the conversion, because 2 to the power of 3 is 1 followed by 3 zeros in base 2. 2 to the power of 1 is 1 0 in base 2. 2 to the power of negative 2 is 0.01 in base 2. And then 2 to the power 3 is 0.001 in base 2. And then you add up these numbers, becomes 1010.011 in base 2. Done. Are there any questions about this conversion process? Yep.
So that roundup will be used to like 375 on the table, right? But like
Yep.
you had like what if it was like 10.376? Would you want us to keep going down?
Okay, so I can change the nature of the question a little bit and ask you what is the closest, okay, binary number with up to 3 digits to the right hand side of the decimal point, to whatever given value that you have. So in that case, you cannot represent that value exactly given only that many digits, but then you have to decide which one is closer. One of our lab activity actually did that. So that's a possibility of a variation of this question. Okay, so any other questions about this one? How the derivation works? Yep.
Just wondering about the wording of the question. Did you ask for each individual step? In my mind, I kind of go to the table.
Show me how you come up with the base 2 representation.
So it's important that we have the step showing the
Yep. So instead of just jumping directly to it's 1010.011 in base 2, I need the intermediate steps. Because I did say you guys can use a calculator that has a binary and hexadecimal capabilities. Now, calculators like that typically cannot help with the fractional part because they can only compute using only integers in base 2. So that's the other thing that your calculator may not be able to help. But your calculator can definitely help you figure out all the powers of 2. That's pretty easy to do. All right, question number 6. There are 7 questions, so we only got 2 more to go. So question number 6 asks, assume we can use gates of any number of inputs, okay? Okay, so first of all, does everybody understand what that means? We are not talking about the width of a gate, we are talking about the number of inputs of a gate. Those things are different, okay? And assume all gates have the same propagational delay. Now, a propagation delay is the amount of time that it takes for the input to settle and the output to be the correct output. So the moment you present all the inputs correctly is the start of the clock, and then you look at the output. When the output is correct based on the input, you stop the clock. The time in between is called the propagation time. Okay? If we know that a 3-bit carry look-ahead adder takes 3 nanoseconds to finish computing the sum and the overall carry bit, so the entire thing, the whole enchilada, how long does it take for a 6-bit carry look-ahead adder to complete its calculation? Explain your answer. Well, the answer is already stated here. So the answer is it's 3 nanoseconds, just the same. Why? What is the whole point of the carry look-ahead mechanism? Doesn't rely on the previous carry, so you're basically bypassing the whole thing about carries. So the other way to answer this question, or the other way to find what the answer is supposed to be, is to go for the definition. Okay, so what definition are we talking about? We go back to binary addition. So we go to binary addition, the notes here, and then we click it, and then we go to the very last part, and then we look at this big mess of an equation, this thing here. My browser took a long time to refresh. This thing here. So if you look at this big huge mess, okay, it looks like a big huge mess. But when you look at the level of gates or the level of operators, it doesn't really matter what n is. It still has the same number of operators. Because this whole thing is really just one single gate. It's a gigantic conjunction or AND gate. This whole thing is one gigantic conjunction or AND gate. The output of each one of the output of this gigantic AND gate is fed into one of the inputs of this gigantic OR gate. So the total number of gates doesn't really change. It really just changes the number of inputs of the gates. It doesn't change the number of levels of gates. Well, if the propagational delay relies only on the level of gates, then it doesn't change. If it takes 3 nanoseconds to compute K3, it will take 3 nanoseconds to compute K6. It would still take 3 nanoseconds to compute K64 or K128. Because all you're doing is to say, oh, this AND gate is now taking in a bazillion inputs. But it's still one single AND gate. The amount of time that it takes for the input to settle, to be correct, to be constant, and the answer, the output to be correct, it's still the same. At least theoretically, based on the assumption of this question. Yep.
In reality, if you have large enough number of inputs, you would split them eventually, right? Because there's an upper limit.
Yep. Yep.
So we're ignoring that.
We are ignoring that in this question, correct. So if I want to make the question a little bit more tricky, then I can place an artificial limit to, okay, so we can only allow up to 2 inputs per gate. So then you have a limitation of fan out. So when you have a conjunction that has 3 inputs, now you have to break it up into 2 levels of AND gates. So the first AND gate would take the first 2 inputs. The output of the first AND gate will feed into the second AND gate, along with a third input to the second AND gate. So now your propagational delay will lengthen, but it will only lengthen in relation to the log of the number of bits. But the question itself doesn't place that restriction, so that means, well, looking at this one, we know it doesn't change the number of, it doesn't change the level of gates. So is that okay? Does everybody understand, this particular question and why the answer is the answer? Yes? Yep.
What's the definition of the level of gates? Because I know as we move up in the amount, or as we move up the amount of bits, right, we're adding more AND gates on a single level.
Okay, so you can compare, just between K3 and K2. Okay, so let's go back and look at K3 and K2. The level of gates means, things that cannot be done at the same time. They have to be sequential, okay? So with K2, G1 can be done by itself. P1, G1 can be done by itself. P1, P0, K0 can be done by itself. But these 3 can be all done at the same time, right? So when these 3 things become available, they all go into the same OR gate, and then the output of the OR gate is the K2. What about K3? It looks a little bit more complicated. But each term of the disjunction, G2, P2, G1, P2, P1, G0, P2, P1, P0, K0, they can all be done at the same time. When the outputs of these 4 terms now are available, they all go into the same 4 input OR gate. So that means, the level of gates does not change, but the number of inputs, does change. The number of gates also change, but it doesn't change the number of levels that is needed.
I see. So we're talking levels, kind of like how we were designing mid-B. Each time you have a new column of stuff. Because with the other ones, you have to put this one, then this one, then this one. But with look ahead, it's always this one row grabbing those 4 things, and then this last and that's the answer. So it's 2.
Right. Yep. Now, it is, and in addition to that, G2 needs its own gate because it's coming from the X2, Y2. P2 comes from X2, Y2 as well, but it goes to an OR gate instead of an AND gate. But that's one layer of gates. So with one single layer of gates, I can compute all the G and all the P terms. K0 is an input pin, so it requires no propagation delay at all. Okay, so the first level would be to compute all the P's and the G's. The second level is to compute all the conjunctions of these P, G's, and the K0. And then the third level is to compute the OR of all of those terms. So 3 levels of gates will compute all the carry bits. Okay? Okay, but wait. The carry bits are not actually the result, right? But the carry bits is a crucial part of the result. What do you need in order to compute the sum? You need a Q, but what is Q? Which is the exclusive OR gate, right? So to compute the Q, you go through one single level of exclusive OR. But while you're doing that Q, we can all be doing the P and the G's at the same time. So if you remember that example, the P, the G, and the Q's, they can all be computed in parallel at exactly the same time. Okay? So by the time the K's are done, then we can go through another exclusive OR. So the K exclusive OR with the Q gives us the S bits, the sum bits. So the sum bits is really just one level more than the carry bits. But it doesn't depend on how many bits we are adding. It's the same amount of time. And that's the whole point of the carry look-ahead mechanism as opposed to the carry ripple mechanism where K3 depends on K2, K2 depends on K1, and K1 depends on K0. Then it becomes sequential, becomes a linear kind of thing. Is that okay? Okay. Let's see, the other tab. And then question number 7. So question number 7, okay, let me cross out the answer first because this one, it's kind of interesting. It's my favorite question of spring 2018 in the first exam. So the question number 7 has kind of the flavor of question 1, but it's not the same. After a binary subtraction, we know the following condition is not possible. B equals to 0, the borrow flag, overall borrow is cleared. The sign flag is a 1, and the overflow flag is a 1. So I'm already telling you it's not possible. There's no question about it, okay? The question is not asking whether it's possible or not, it's telling you it is not possible. But it's also asking you to explain why this is the case, why it is not possible, and it's giving you a clue of where to start. Use the definitions of the borrow, difference, overflow, flags. Okay, so start with that. Okay, hint. Okay, so when I use the word hint, I would pay attention to it, but it is your choice whether to pay attention or not. Hint: a state combination of 2 of the flags implies the value of the third flag that contradicts the given condition. So it's a little bit vague, right? Okay, but it does tell you something about, if you look at the combination of 2, it automatically says the third one has to be something. And it is contradicting what we are trying to display here. And then a little bit more, think of the definition of the overflow flag, the sign flag, and the borrow flag. So after reading the question, including the hints, what are you going to do? Let's say you only got 5 minutes left at this point. What are you going to do? Based on what I say here, based on the hint, based on what I say, think of the definition, What are you going to write down in 5 minutes? You know you're not going to have enough time to finish the entire question, but you have 5 minutes. What are you going to do? Write down the definitions. It is me screaming at you and say, please give me an excuse to give you some partial credit. Well, it depends. It's probably not a passing grade for this particular question, but it'll be some points, right? I mean, some points is better than no points. All right, so I'm going to answer this question. So let me set up the tablet so that I have the question itself. Borrow is 0, sign is 1, overflow is 1. Okay. All right. So the first thing is to write down the definitions. What is the borrow flag? Did I mention it's a 3-bit by 3-bit? Nope. Okay. So if it doesn't say it's a 3-bit thing, then you just have to say the most significant bit. Okay. So you can say now, you can also assume, okay, assume this is a n-bit subtraction. So basically all we need is just to have a term that we can refer to as the number of bits so that we can designate the sign bit of the components. Okay. And it's x minus y. Okay, so that makes it extra clear. All right. Which flag do you think I should start with? Well, I mean, they're all about the same. The overflow flag is actually very easy to define. Okay, so you can choose to start with the overflow flag. The overflow flag is x n minus 1, not y minus 1, and not d n minus 1. D is the difference. So I'm using the very same terms that I use in my notes. Remember in the notes, I have x as the minuend, y as the subtrahend, q as the partial difference, t being the row of all the borrows, and then d as the row of the difference. So if you use those same terminology, you don't even have to define those because it's consistent with the letters that I use in my notes. Okay. But that's not all. There's a little plus here. Not x n minus 1, y n minus 1, d n minus 1. Do you guys briefly remember this thing? Okay, this is from the notes. Okay, this is from the modules. Okay, so O is defined. What about the sign bit? Oh, okay, so given these terminology, the sign bit is easy. Which one is it? It's already in the definition of O. It's one single term. Whose sign are we talking about when we talk about the sign bit? Are we talking about the sign of the minuend, the sign of the subtrahend, or the sign of the difference? The sign of the difference. Okay? So that would make it dn minus 1. Cool. And what about the borrow flag? The overall borrow flag is Tn. Okay? But you know the definition of Tn. It is the b of x n minus 1, y n minus 1, or the borrow of q n minus 1 and k n minus 1. Oops, not k. Okay. It's not k because it's t. It's k for addition, t for subtraction. Okay. Partial credit already. Nice. Okay. So given you have more time than just writing down all the definitions, which one are you going to nail down first? Which one you go like, yeah, we know that thing. We know what that is. Which one will give you the most clues to answer this question? The sign bit, right? Because it's not even an equation. All it is saying is we confirm that the sign bit of the difference is 1. Okay. So we say, sign bit is a 1 implies dn minus 1 is a 1. By definition, that's the definition of the sign bit. Okay, so if that is the case, and we know the overflow is a 1, okay? Now the overflow is also a very restrictive definition. Because if you look at the overflow, they cannot both be 1s. Okay, the conjunctions of the disjunction, only up to one conjunction can be a 1. So that means if the entire thing is a 1, we can nail down which one is a 1. So if we already know dn minus 1, d subscript n minus 1 is a 1, that rules out the left-hand side completely. Because the left-hand side has the negation of dn minus 1. If dn minus 1 is a 1, the negation of that is going to be a 0. That zeroes out the entire left conjunction of the definition of overflow. What are we left with? The right-hand side. Okay? So this further implies, okay, the overflow is, we know that the negation of n minus 1, the non-negative version of y minus 1, and the non-negative version of d minus 1 is a 1. How is that going to help me? Well, that nails down every single bit, right? Because in order for this entire conjunction to be a 1, I already know d subscript n minus 1 is a 1 already. What else need to be 1s and which one has to be a 0? X has to be a 0. Exactly. Oh, wow. So this further implies x n minus 1 has to be a 0, y n minus 1 has to be a 1, and just to repeat myself, d n minus 1 has to be a 1. I know exactly what the last column is going to look like in the subtraction. Okay. So that explains the overflow. It explains the sign. Now we look at the borrow. Okay? So you look at this combination and you ask, why is the borrow being a 0 not possible? Yep.
Is 0 and y is 1.
And the b function applied to that is a 1. So that guarantees the borrow flag has to be a 1. And that is why this combination is not possible. Because the fact that the sign is a 1, the sign of the difference being a 1, and the overflow flag is a 1, guarantees the borrow flag to be a 1. There's no escape from that outcome. So is that okay? It's all based on the definition of the terms. There's nothing here that is not in the definitions of the terms. Yep.
Let's say you don't even have time for definition. Can you just give me like one example of the question?
Say that one more time.
Like you don't even have time, right?
Well, you cannot have an example when it is not possible. So the only way to do it by example, there's no way to do it by example if I do not even tell you the number of bits. But if I tell you ahead of time, consider a 3-bit subtraction, then you can give me a table of 64 test cases and show that none of those 64 test cases yields a result of what I state here. Huh? Okay, so I'm assuming the other way around means, I want to prove a particular thing is possible. Then you can give me an example. Yes. So is that okay? That's all. I mean, this is question number 7, which I think is my favorite. But there's a reason why I put it out as question number 7, because I think most people it will take a little bit more time to reason this one out. But you can see how I really just start with the definition, and it's basically constraint-based thinking. You look at the definitions, you look at what is given to you, and you say what of the given facts combined with the equations, the definitions, will constrain the most possibilities. Apply that one first. Lock it down. Then you look at the remaining possibilities and you look like, okay, so how can I further perform more restrictions and use whatever is given and all the equations. So I can only explain up to that part of how I reason this thing out. So even though this is a question that I ask, a lot of times I ask questions that I do not have the answer to yet. So I would just throw out some random bits and go like, is that possible? Okay, then that becomes an exercise for myself and go like, can I come up with an example to show it is possible? Okay, work it out. Yep, it's possible. Or after a while, if I cannot figure out that it is possible, then I go like, well, doesn't seem like it's possible, but can I prove it is not possible? Then I go through the process that I just went through here and see if I can prove that it is not possible. Now, when you explain this, you don't have to use the implication symbol and chain the reasoning like mathematically, but you do have to explain the same thing. Okay, basically you just start with something and go like, but if that is the case, this has to be the case, and if that is the case, that has to be the case. If that is the case, that has to be the case, and so on. So you can use English if you want to. You can use mathematical symbol intermixed, with sentences. That's fine, as long as the chain of reasoning is clear. Is that okay? So given that, so in our test, there will be some double precision floating point number thing that I'll throw in because we have talked about that already. It's just that the conversion process has not been finished yet. So there will be some floating point number questions that I will also include. So given all of this, how are you going to prepare for the exam? Okay, so there's the second question. How do you study? That's a good answer, as opposed to okay, I'm not going to say that it's not politically correct. So yeah, something just kind of popped up in my mind and go like, wow, okay, should I say that? No, okay, let's not go there. Okay, so studying is good. So, but how do you study? Because I have seen studying and I've seen studying, okay? In elementary school, middle school, and possibly a good portion of high school, studying is memorization, right? You go through the material enough time so that you can actually remember, phrase by phrase, sentence by sentence, symbol by symbol, what the textbook has already introduced. That is not going to be helpful here because it is open book and open notes. I'm not testing whether you can memorize, okay? I'm testing whether you can apply what you have learned to solve a problem that you may not have seen before. So in addition to going through the notes, which is probably a good first step, how do you go through the notes? Instead of memorizing, what do you do when you read the modules or when you go through the recording of the class lectures and whatnot? What do you do when you're doing that?
One of the things I do is I print it out and then I go through it and look at and underline or sticky note anything that might be useful.
Mm-hmm.
And so, like for example, like definitions of things or like.
Right. Okay. So very good. So definition of things is going to be important, okay? Because those are the things that is unquestionable, okay? What is the definition of the borrow flag? Okay, it's in the notes, okay? But some of the definitions are kind of hidden in a very obscure way. So if you want to look up the definition of P and G for addition, it is hidden in a paragraph that is not obvious at all, okay? So you might want to kind of highlight that, okay, or use a little post-it, next to your notes and go like, this is where P and G are defined, okay? So knowing where to find the definitions is going to be helpful, and it's not going to be easy if you do not go through the material at least once yourself, okay? What about the reasoning part, the explanation of things, the reasoning part of my notes? Yep.
What kind of like strategy when you like when I watch the recordings,
Mm-hmm.
I just like copy the question into a scratch paper and
Mm-hmm.
try to like do the reasoning on my own, like see
Yep.
if I can go through all of them and write the reasons for it in terms of like mathematical explanation.
Okay, so you're talking about just going through the questions,
It's like we did like the
Mm-hmm.
and the K,
Mm-hmm.
like that they cannot be like both at the same time. Like
Yep.
one, so that's something like a good example.
Yep. Okay, so what if you encounter, now this part is difficult for me to explain. When I was a student, and in these days I still study, but not in the sense of studying for exams, but I still learn new things. But I can find out things, I can feel that I do not fully understand something. It's really hard to describe it, as a spider sense, trademarked. As a spider sense, I can be going through something, an explanation. All the terms are common words, okay? But in my mind, I just have this kind of gnawing feeling, go like, I'm not getting it. There's something here that I do not fully understand. And then I'll just kind of look up the terms and say, okay, how is this term defined exactly? What does it describe exactly? How does it fit in this sentence with all of the other terms that I already understand? And so I'm not really just reading the sentence and memorizing the sentence itself. I'm trying to connect the concepts using concrete logical connections. And if I cannot establish that really, really concrete, solid, rigid connection between the terms, my mind just wouldn't let go. It's like, okay, I gotta get this one. I gotta get it clarified, to the best ability that I can. Now, it's a process, and it's also a hunch that is really hard for me to describe. And I suspect that most people have that hunch too. It's just that some people choose to ignore that hunch. It's like, I guess it's not important. I'll just kind of move on, or I'll just remember what the sentence is, and I think that's good enough. So, I think that is important, when you're in a class like this, and also when you're at work. So if your boss, just suddenly come to your desk or ask you to go to his office and go like, we're gonna have to re-implement this using Google Cloud, platform, and you're in charge of this project, and go with it. Tell me what you have done at the end of the week. Okay? Your boss is not explaining anything to you. Your boss is not sending you to training. Your boss is asking you to investigate how to make it work. Okay, and just pointing in a very general direction. Okay, that's the general direction. What are you going to do? You're not in the class. You cannot go talk to the professor. So you kind of have to go through the whole process yourself. Okay, and I find that it is important in the process to really kind of stop whenever I have something that I'm not really clear about. Stop, look it up, and make sure that I have a really good understanding of the term before I proceed. Okay? So I can only describe up to that point, of how I study or how I read material that I think is important in classes like this. Whether it's going to help you or not, or whether you need that help or not, I don't know. Okay, maybe most of you know this already. Maybe most of you can study better than I do when I was in college anyway. So, I'm just, telling you something about my thinking process. Any questions, comments? Please don't tell me anything about your own thinking process anymore. Yeah? Not with this one. Yep. So no C++ code, but the notation of C++, you should know it, because we have used the ternary operator to express some of the terms already. So that is the one thing that you do have to understand. So when we talked about signed versus unsigned numbers, the value represented, I used the sigma notation, the sum notation, and also the ternary operator. Those can potentially be in the test because they are actually in the material that we have covered already. Is that okay? Do you guys know which part of the notes I'm talking about? Okay, let me go back and locate that so that we know, what can potentially be in the test, even though it is not in this particular actual exam one. So when we talked about signed representation and comparison, that's when we introduced the sigma notation and the ternary operator and stuff like that. So let me go back to that notes here. That thing. Now, will I ask you to make derivations like this? No. Do you have to understand, the final form like this one? Yes. Okay? Do you have to understand what this means, what that means? The value represented by a bit pattern? Yes. This is for signed, and it's different from unsigned interpretation. They're only different by one single term. Oh, that's the proof of the other one. Oh, where's the other one? Unsigned value. I think that one is in the base conversion notes. So let me go back to the base conversion one. I don't know how many of you have printed out all the modules. That can be helpful. You know, having all the modules available during the exam can be helpful. So we talked about base conversion. Where is it? Right here. And in the base conversion one, there are a few equations that I think is kind of important. This is one, okay? So this one, when b is 2, it also can be used to explain how you get the value of a binary number interpreted unsigned. Okay? So this is one kind of useful equation. And then the other one is to how to extract a particular digit in the base. So this is the other equation that can be really useful. I being the digit destination, D is the value of a particular digit at position I, V is the value that you want to express, B is the base, and mod is modulus. So this is also a kind of useful equation because you can use it in base conversion, but it also kind of gives you an idea of what digits really represent in a number. So all of these things are kind of important, even though none of this was in the practice exam. They are still useful. I'm still assuming that you understand these topics. All right. So let's say that you went home, or you immediately go to the library, you study, and then you encounter something, go like, whoa, I totally forgot about this, or not really quite sure about that, and then you re-watch the videos and it's still not clear to you. What are you going to do? Yep. That's why you have 1 week until the actual exam. We have one class meeting in between. So if you find anything, if you have any questions, you can contact me before, or you can ask it in class. But I'm giving you, in my mind, plenty of time to study, find out what you do not yet understand, formulate the question, and then ask me before the actual exam. So use that time, to kind of go through the material, and bring the questions to me one way or another. Beyond that, I don't really have much else to say. Any questions from you guys? The lab today is really just the continuation of what we started on Monday, because the stuff on Monday has a due date of tonight. So it's just a continuation. If you guys are done on Monday, there's nothing else, that I have scheduled. Because I haven't really talked about the extra stuff, that's in the next lab. The next lab is done already, but I'm not releasing it because I haven't really talked about the material that you need. Is that okay? All right. So we are going to transition to the lab. If you have nothing else to do at the lab and you want to go get lunch, that's fine with me. If you want to start studying and during the lab time and ask me questions as you study, that's a good use of time, good use of your time, and good use of my time. So it's entirely up to you to kind of determine how you want to use the lab time today. So I'm going to go over to the lab as soon as I clean up here.